So welcome everybody to the beginning of our fall Big Data Hubs, Cyber Infrastructure and Data Sharing Working Group. We're joined today by three folks who are going to talk about a topic near and dear to my heart, having come from working with the Hubble Space Telescope Archive and doing a lot of preservation around data and how we do all of that. This is an important topic that often sort of gets a little overlooked because people think it's a simple process. So we'll sort of hopefully have maybe 10-15 minute talks from folks and then leave some time for questions somewhere towards the end. So why don't we go ahead and start off. I'll go through we'll go through the order that they're listed here in the bios. So first up is Shawn McKee, who's a research scientist in the University of Michigan Physics Department and the founding director of the Center for Network Storage Enabled Collaborative Computing Sciences as part of the Michigan Institute for Computational Discovery and Engineering. He's part of the Great Lakes Atlas Tier 2 Center, which is part of another experiment producing oodles of data, I would say, and preservation of that is sort of important as well. But this is part of the ATLAS experiment coming out of the Large Hadron Collider at CERN. Since 2001, he's been the network project manager for USATLAS, planning for the development of necessary network environments to support the computing model. He also co-leads the USATLAS Facilities and Distributed Computing Area and the ATLAS Distributed Data Management Area. So a lot of work going in behind all of that data and getting all of that processed. Since June, he's led an open science grid network area. He's the principal investigator of several projects, including the Multi-Institutional Open Storage Research Infrastructure, or MI-OSiRIS, SLATE and mobility capability, and NetBASILISK, which is the network at broader scales, integrating and leveraging individual security components. So with that, and with a lot of good information around all of that, I'll turn it over to Scott or to Shawn to tell us about all the data preservation things he's doing.
Okay, so I guess for me and probably for everybody on the call, data is one of probably the primary challenges we all face when we put together, large scale cyber infrastructure. We always can, and we continue to have problems. So, in the project that was mentioned, OSiRIS, we tried to put together a multi-institutional, multi-science domain storage infrastructure to let people share and directly access data. And so that project just ended at the end of August. We're continuing to operate it with help from our institutions. And so this sort of touches on one of the challenges, one of the aspects that we have to worry about, which is how do you continue to provide capability services for the foreseeable future. Data isn't going to go away. It's going to keep getting larger. It's going to keep presenting us with significant challenges. And there's all these questions around data provenance, data lifecycle management, how you actually keep track of all the data that you've generated, how you reliably store it and provide access for it into the future. And I have to say that I obviously don't have any answers here. I've seen a lot of the challenges. I'm constantly thinking about how we might do this on a large scale. For the ATLAS experiment, we have, as mentioned, huge amounts of data. We'll be producing, by the time of high luminosity LHC, 0.5 exabyte of data a year just for ATLAS. And that's just the data. Then you have to have the simulations and everything that goes with it. And where do you put that indefinitely? So, for the Large Hadron Collider experiments, what we've done is invested heavily in large back-end tape systems, right? Tape still is the cheapest way for us to store these things long-term. But there's a cost to keeping that indefinitely and to cycling onto new media as you move forward. And that's one of the things that we're continually looking into, and still for now, We rely on CERN and 10 or 11 large tier 1 centers around the world to provide these big hierarchical storage management systems based on tape and some fast disk on the front end and some other technologies. And, you know, that works, but, you know, there's a cost. And so these labs have to commit to each one being a steward for, you know, CERN has a complete copy for each experiment of all the data. And then these other distributed tier 1 centers, national scale centers around the world, each take roughly 10% of the data, and they're responsible for that. And what responsible means is, of course, keeping a copy for the future, but also if data has to be reprocessed, new calibrations come out, new methods, and the data has to be converted back into something new, then that's the responsibility of each one of those sites. So that's part of being a steward of the data, is if there is actually still active use of the data, somebody has to provide the ability to actually process on it, transform it, you know, apply new algorithms to the data based on new discoveries in, you know, how we do reconstruction, how we do calibration, et cetera. So there's a lot of topics here. I don't want to talk for too long, but I also, you know, there's a bunch of other projects that I'm involved in, and I have to say that, you know, data is one of the big challenges in all of them.
So I fumble through windows. Thanks, Shawn. Yeah, you touched on many of the topics that I'm very familiar with, including, you know, long-term storage is not a static thing, really, is sort of the other point. So maybe we can come back to that in just a little bit. All right, so next up is Dr. Henry Neeman, who is the director of the Oklahoma University Supercomputing Center for Education and Research and executive director for research computing, associate professor in the College of Engineering and adjunct professor in the School of Computer Science, all at the University of Oklahoma. He and Dana Brunson have been appointed co-leads of the XSEED Campus Engagement Program, which includes mathematics from the state, which includes the Campus Champions, which is a great program that really helps bring cyber infrastructure across to many people across the country. He received his Bachelor of Science and BA in Statistics with a minor in Mathematics from SUNY Buffalo in 1987. His Master of Science in Computer Science from the University of Illinois Urbana-Champaign, and PhD in 1996. Prior to OU, he was a postdoctoral researcher at the National Center for Supercomputing Application at Illinois, and served as a graduate research assistant both at NCSA and for the Center for Supercomputing Research and Development. In addition to his own teaching and research, he's collaborated with many different research groups applying high-performance computing techniques in fields such as numerical weather predictions, bioinformatics, genomics, data mining, high-energy physics, astronomy, nanotechnology, the list goes on and on. And he serves as an ad hoc advisor for student research in many of these fields. His research interests include high-performance computing, scientific computing, and distributed parallel computing. But I also know Henry is involved in the OurStore project, which is a long-term data preservation project funded by the NSF. So I will turn it over to Henry to tell us about data preservation from his point of view.
Thank you, Niall. And if I'd known you would read the whole thing, I would have written a lot less. Okay,
that's all
can
right.
I do a quick share screen?
Absolutely.
I think you have to make me a co-host.
That would be Chris's job.
You should be able to.
I'm gonna try. Oh, maybe. Oh, there we go.
Yep,
Right, you are. Okay. Can y'all see that?
Yes. Well, we can see you started. There you go.
Okay. All right. That's just a title slide, so don't worry about that. At OU, we are so dumb. We are deploying 5 major systems at the same time. So I just wanted to point that out. So any slowdowns in getting stuff out to you all is because we're trying to do many, many things on very limited time. So the project we're doing at OU is called the OU and Regional Research Store. It's basically a giant robotic tape library. So it was delightful to hear Shawn say that tape is really important. tape is not important because tape is good. In fact, tape sucks. But tape sucks the way democracy and old age suck. It sucks except compared to the alternative, because the alternative to tape is not disk. The alternative to tape is throwing the data away. And there's a very simple reason for this. Disk is terribly expensive, and relatively speaking, that's only going to get worse. And what I mean by that is disk is improving by a factor of 2 every 5 years now, whereas tape is improving by a factor of 2 about every 3 years. Not as good as the good old days. Disk used to improve by a factor of 2 every 14 months, but that's far in the rearview mirror now. So for our store, for this tape archive project, the business model is a business model that makes archiving affordable. The problem with archiving is that archiving is expensive, but in the sense that there are giant fixed costs. Tape systems, the hardware and the software, are terribly expensive, and they're terribly expensive before you put the first slot for a tape cartridge on the floor. We found that over 80% of the hardware and software cost we had was fixed costs that came with 730 tape cartridge slots. And then adding more slots after that was super cheap. So we have an NSF grant that pays for the hardware and software and the initial warranties. Our CIO covers the mechanical space power cooling network, and then also the labor as part of the cost share. And then he also picks up the annual support after the initial warranties expire. So what do researchers pay? They just pay the incremental cost, which is the tape cartridges. So researchers buy tape cartridges. They don't buy anything from us. We never touch their money. They have the tape cartridges shipped to us. We pop them in the tape archive. And that is super cheap. So LTO, actually, when LTO 9 was released a couple of weeks ago, LTO 7 tape cartridges came down by about 10% right around that same time. So they're now about $6 per usable terabyte per copy, or $12 for dual copies, which is usually how we present it to people. And you know, tape lasts a long time. So when you stick it in the tape archive, it's there for the life of the archive. Now, Shawn's point about later moving it to better, more recent versions of the tape, that is a point well taken, but we're not doing that all the time. We do it once in a great while. In fact, we're just about, on Monday, we will start doing it here, copying from LTO 5 and 6 to LTO 7 type M. I'm not going to go into too much detail. So we're starting with 11,000 tape cartridge slots, because the difference between under 1,000 slots and about 11,000 slots was a very modest amount of the total budget. As it turns out, we're actually able to add another 11,000 slots at another campus about half an hour from here. And we'll be doing that in the coming year. We're starting with 6 drives, gives us a little under 2 gigabytes per second aggregate bandwidth. But that's pretty good for what people need. And then we're going to add some more tape drives of later flavors later on, depending on how many no-cost extensions we can get approved on our NSF grant. We've got about half a petabyte of disk as a front-end landing pad. And we are making sure that the secondary copies live on the other campus, not in the tape library. That would be a complete waste of tape cartridge slots, but on shelving units in an environmentally controlled room, so that we are actually doubling not just the number of slots, but the actual capacity for content by putting in the second tape library. Keeping the secondary copy inside the tape library to us looks like a waste of money. And then what kind of features are we adding that we didn't used to have on our old tape archive? One thing we're doing, we haven't written the script yet, although we have sort of a design for the process, is auto archiving. So when a user drops a file into a particular directory, a daemon script comes along, notices it's there, and automatically archives it to tape. We could have used expensive commercial software to do that, but it would have been expensive and we're always broke. So we're doing that by hand. File sharing, we've got a Globus license that we just got actually a temporary license until we get the paperwork worked out, because we're doing the HIPAA version with the BAA. That's got to go through legal, you know how it is. But so we've got Globus file sharing is something we'll have in production in the next few weeks. Caching, we didn't used to have the ability to do this, but now if a file is popular, it'll stay on disk in addition to being on tape. If it's unpopular, it'll be on tape only. We're just using least recently accessed as our mechanism for that. If a user is really itching to make sure that a file of theirs is always on tape, they can buy disk. We're just not recommending that. We don't expect a lot of uptake because it's a whole lot of money and honestly not that much value. And then the price, I mentioned the price per terabyte has come way, way down. And I think will continue to fall. We're expecting LTO 8 to be break even with LTO 7 type M sometime in 2022. And as soon as it is, we'll start discouraging people from buying the old one and encourage them to buy the newer one. What we have seen historically is that the most recent version of LTO costs roughly twice as much per terabyte. So we never, ever recommend the most recent version of LTO, even though it would save us on tape cartridge slots, because our users would be pissing their money away and then they would be mad and stock off in a huff, and we don't need that. I think that's pretty much it. I do have a slide on our disk stuff, but that's not really relevant here. So anybody who wants it is welcome to it. And there's a much longer version of all that stuff available on our symposium website from just 2 days ago. So
Thanks, Henry. And you didn't mention that all of these deployments are also going on during this wonderful COVID season with part shortages and all those sort of things to contend with. So
yeah, the latter part has been,
as usual.
The latter part has been a big deal. The COVID thing has not really affected us that much because the number of people who are in the data center at any given time is really low.
Sure, absolutely. All right, and let me introduce our third presenter today. Our third panelist is Scott Yockel, who joins us from Harvard, where he's been leading the HPC group in science and engineering since 2015, and is working now in the University of Research Computing Office. He's been on both sides of HPC, both as a researcher and administrator, so he has that understanding of you know what it is to actually work with data and work with modeling. His research domains include computational chemistry with overlaps into material science and mechanical engineering. He's involved also in the Campus Champions project and is co-PI for the Northeast Storage Exchange, the New England Research Cloud, and the CI Center for Excellence, creating a national research computing data center and resource center. So why don't you jump on in and let us know about sort of the aspects of data preservation you have in your hands.
Sure. Let's see if I can share here. And I will warn you, I'm on campus and I'm using the Wi-Fi. And like a lot of campuses have been using the new Aruba setup, it's hit or miss if the patch each week is working. So I want to preface that. It's actually my first time to be on campus in an office in 18 plus months. And in 30 minutes, I'm having happy hour with my group for the first time in like 20 months. So anyways, today across Harvard, there's a very disparate kind of understanding of data and usage and what that is as a problem. I've learned a lot through collaborating with Mercedes Crosses over the years, who's the kind of lead PI on Harvard data on Dataverse.org, but also helps run the Harvard Dataverse. She just recently took a position this summer back into, she's actually a secretary of open data in the new Catalonian government. Anyways, so I've learned a lot in that space. And what's happened is through kind of an evolution, there has been a much tighter knit thing that's happening between research computing and our library. And that's kind of what I'm going to talk about a little bit today. So I have a few slides in that space. So one is around the problem. So typically the friction happens when researchers would like to collaborate from different institutions, right? It's not easy. They each have their own data collections, right? Whether they're, even if it's open data, the data sources and all that they have, it becomes even more problematic when there's data use agreements, when you have IRBs and stuff like that. There's a lot of regulatory problems about getting across multiple institutions in that space. And then the idea that we're collecting data from different experiments and observations. I grew up in the sciences and I was a theoretician for the most part. So this to me didn't seem like a big deal until I started engaging a lot with more social scientists and stuff. And so like where they pull their data, what do they call their data set is a whole different idea, right? It's a much different refinement until you get to the data set that you would actively do research on, which becomes the analytical data set, right? Because this data is all messy, right? For most of the scientists, this data is really clean for the most part. And so you get in this messy space where you actually get to clean data and then do the analytics part. And then when you're different institutions, right, you have different analytic platforms, they're not the same. And then maybe you publish to a data repository, but you have a data repository that might be way through library. It's not the same data repository maybe that your researcher has access to or the thing that they're publishing to. So that creates a lot of duplication of data sets across different sites. You know, we know all these kinds of problems regularly. So inside of an individual institution, we may be able to have a lot more control, right, around data collection, have a data use agreement system that the contracts go through, understand who has access to that data. We can have some kind of interoperability space that is, say, the research computing cluster or some specialized secure enclave that we onboard multiple different groups to. This thing in the middle could exist on our campus. It could exist as a shared infrastructure, a cloud resource or something like that, right? But I think the thing that's still a friction, even on our internal campuses, is that the tooling that we have to do these is all separate. They're all normally different pieces of technology. And then to a researcher, this creates a lot of friction in their process and they get really frustrated. And I think this is where we have not collectively done as good a job as we should. And then look at other tools that they use like Google Docs, right? Great way to collaborate. Google Drive, super simple for them to engage with. We don't have the analogous of those on our large campus infrastructure. And I think that's the kind of next tranche of work to do and not think about them as an individual thing. Like we could put open on demand in front of our HPC system, that's great. But if it's not talking to the data publication space, if it doesn't understand the DOA system, then all these things become kind of very manual, labor intensive, different communities of people that a faculty has to engage with. And that's kind of the problem currently. So if you were then going to have them do that same type of thing at a different institution, there has to be some kind of sets of standards to do this same kind of tooling across multiple sites. And that's when you get kind of into a federation of services. And that's where kind of a true global solution of data commons. And there has been people that have thought about those types of things, like the NIH spent quite a bit of time thinking about that across their various different institutes. So today I'm just going to share a little bit about what we at Harvard have kind of aspired to do in that space locally as kind of a pilot project that we got some funding on internally. We also just got awarded an NIH grant to be one of the generalist repositories. So there's additional work that we're doing to meet those needs. We also had a workshop that a few of you, I think Jim Mugamush was on it. This was like years ago, but I think it was just barely like 12 months or 10 months ago, where we thought about what are all the other projects that are out there and people, what are their concerns in this data commons space? And so at Harvard for more than 10 years, we've had this project Dataverse. There is a local installation that is Harvard Dataverse, and it is the largest of the different, I think there are like 120 different Dataverse installations worldwide. So it has a pretty extensive size of data set. It has quite a bit of downloads. This is also like a year-old stats, so it's a little bit more than that now. But there is some limitations into the code base. It's set up, it was designed for social science stuff. There are some places where it kind of is challenging for large scientific data sets. And that's one of the things we're trying to overcome because the mechanism to move data currently is just through a web or a web API. So Globus will be a big part of putting the front end and how you upload and download data into Dataverse in the future. Anyways, so in this diagram, simply there's data acquisition that happens. We have data analysis, as I alluded to before, and then we have this publication space. And right now, the only place that Harvard Dataverse is engaging in is this last part. So it's an afterthought in the process of research that somebody thinks about, how should I tag my data? How should I represent versions of this data along the way in the data analysis phase? So what we'd like to do is create a set of tooling so that they can check in these raw unpublished data sets, right? If needed, they can get a DOI, but there at least is metadata that's represented to them. This metadata is really, really important because it would represent the state of the data, but we can also include things like the code, the container, or other artifacts that are part of the data analysis process, like maybe the data workflow, like using DAG and other common workflow language, those types of things to check in with the data source. So that rich metadata now represents really the provenance. We can then now use this metadata with a variety of different tools and things. So on the left side is trying to represent what kinds of tools exist in the data analysis space that we want to integrate with. So our space is one that we are trying to integrate Dataverse with, which is an electronic lab notebook. So that's the space where they're explaining what they're doing, right? It's not a place in which the computations are happening. The computations happen through a number of, what are becoming the most common platforms, with is the Jupyter Hub and the RStudio, as well as you could probably throw MATLAB in there. So if we can start to use and connect what's happening in this space with something like a repository-based thing like Git, then we can string together all the versionings of the code base or the container along with the data as it goes. And you can use something electronic like RSpace to have a comment on your process. So we're connecting kind of the thinking, and this RSpace also has the ability to have kind of the faculty PI approval, like, or call and response space of comments. So there's kind of an enriched kind of interaction that can happen now between tools, and we can capture those because they are just data. We can capture those in a repository like Dataverse. So I already talked about Globus. We know Globus can be used as a data management system. It can also be used for sharing, but kind of the thing that's lacking is you don't go to the Globus interface and search for data, right? You can find an endpoint, you can find a shared endpoint or a managed endpoint. And so to be able to integrate the metadata part that we have in something like Dataverse, so that you can find the data, and then instead of it being represented as a zip file that you're going to download via the web, you could actually have automatic created shares that happen in Globus. So that's one of the other integration points that's underway. So one of the pieces, and this is what Henry just alluded to, is like policy-based engines. It happens to be that the Cambridge computing folks are literally in our neighborhood, so we talk to them all the time. And we finally, I guess, over time have gotten worn down enough where we're engaging with them, and actually for the first time after using Starfish for 3 years, I think across the university. My department, Faculty of Arts and Sciences, Research Computing, the medical school, and the libraries, they're all using Starfish in a variety of different ways. We also had our first kind of Starfish user group meeting, which was, information that I had talked to other users, and we decided to do it ourselves as a grassroots effort. I would say that there is a vibrant, rich community among various different universities, as well as a lot of kind of biotech people, where you are starting to be able to do some pretty interesting flows of data by tagging or creating policy. It's still lacking a lot on the end user space. There is an end user portal. One of the things that we're doing that will be nice is that every end user has their own zone, so they can only see their data, and they can create metadata and tag things. And they will have tooling that is not the command line interface to run DU and wait till tomorrow to see who's using what. They'll have instantaneous access from a database about data in a much grander scheme with visualization. So you could choose lots of different solutions here, but this is meant just to represent. You need something like that that's not a command line interface, because there are so much better tools in the cloud space that they become accustomed to. We have to provide them that. They also just shouldn't be using command line to move large amounts of data around anymore, right? So that's kind of our idea, and I'll spend a couple more slides talking about this. What is the storage tier 3 space? Because this is something new that we didn't have before. Tier 1 is, like adjacent to the high performance computing. Tier 2 would be like kind of your generic NSF file system. We've replaced this NSF file system with Ceph, and has become a way in which we create a large individual file system, but then partition it out and serve it out via RBDs, and then make that be NFS or Samba. And that's just a nice way to get rid of the individualized management. So a couple more slides to talk about the tier 3. So as a part of both that tier 2 and tier 3, there is the New England Storage Exchange project, which is one of the DIBBs project. And my group has been kind of lead at running the backend engineering on it. It's a collaboration across all of the schools within MGHPC and MGHPC as an entity itself. So here's the co-PIs. And just giving you 2 diagrams here to finish off what we've been doing. So we do have a large Ceph data lake, and one of the interesting things when you provide data as a service across multiple institutions is that identity management becomes a real tricky piece. So it was either bite the bullet, run our own local federation identity where every AD across not just a single university, but could be across lots of different parts of the university. We have to tie into some centralized identity management for MGHPCC, in which there are at least 20 to 30,000 individual users across right now on our systems across different schools. That didn't seem like a good idea to try to do. So what we did is we completely abstracted the idea of the user identity from the data. So data is represented, and Ceph, it can be represented to the data transfer node via CEPHFS, and on the tape system that we just employed. So this is a IBM TS 4500. It's about 130 petabytes of capacity with 1 petabyte of spectrum scale on the front end. Anyway, so that's also mapped up here, the data transfer nodes. So what's interesting is that it turns out the only people that really need access to the data transfer nodes are not the actual end users, not the researchers. It's the tape owner or the media owner of Ceph that have added stuff. So this is the other research computing admins, right? So the NSE engineers, which is really one person, engages with this team of like 15 or so tops, and they can log in directly here, and they can create a Globus share, that they can see as the managed endpoint. Then in the Globus sense, they can then share that out to any Globus ID. So they can add the PI as the data manager, and then they can do what they want with it. So in that point, it becomes their own internal research computing group, say from Boston University and their community, to manage how they want to do this process. It allows us to scale this to really just only a couple of different storage engineers on the background, in the backend, managing what is a huge amount of storage. And so that means that we've really just kind of made this like a cloud resource. So they can hit this resource right with an API if they wanted to, then from their HPC system, they can move data in and out. So it's not meant to replace like your high performance computing attached storage. It's meant to be like that next step, that kind of large scale, cheaper staging storage. And so relative cost wise, the tape stuff is about $5 per terabyte to operate. And the Ceph storage is on the order of like $40 per terabyte per year to operate. And then your high performance stuff might be a little bit more, maybe it's like $100 per terabyte per year, depending on what you're doing, if you have any other costs. So what's interesting is that this solves it for that kind of POSIX use case, but then, whoa, it dropped out of the, sorry about that. I clicked on the diagram and then it went to the, but if you wanted to create an S3 bucket, so you have like global namespace, there's a cool piece of code called Minio. You can run it in a very similar fashion. So we have CEPHFS and we have GPFS on the back end. And so when we're mapping, like on this instance, like we'd have like a tape pool, we map that to the data transfer node with a file set, which has, we can map that then to Minio in either 2 mechanisms. We can create a Minio tenant space, which is kind of a namespace that then this person here, the tape owner or the RC provider, they're like, they have an admin interface, and then they can create buckets however they want. And they can share one large tape pool or one large disk pool and share out buckets and access keys. So what we've done is completely separate the user from the data as far as the management of it. And what happens is they have access tokens. So it's at this access layer is where the identity of users exists. And so that's kind of been an interesting thing that we've done. And one of the places that's been nice is that Like at Harvard Library, they have a digital repository service, which is like part of their archive service. And their requirements to do archiving are 2 disk copies and 2 tape copies. So they were managing all the infrastructure themselves. And as they've transitioned onto different services, they're now using S3 as the mechanism to store data and transfer data and access data. So they're able to leverage the Minio system here, have a copy on tape. They leverage Iron Mountain, who has an S3 bucket front end. And so now they have tape in 2 different locations. They also use another S3 mechanism with us for disk. And then they also manage their own Isilon with their other disk copy. So by doing that and leveraging some research computing infrastructure, as opposed to enterprise IT infrastructure, which is managed and run in a different manner, they're able to reduce their cost to store data in half, which is a really important value to what is the archiving part of Harvard. So that's just kind of an example of things that we were interested in, things that we find a problem, and not necessarily like 100% solution, but we do have some building blocks. I'd like to think that, especially like from this, we are working on various different components of this and building blocks. We're hoping to get to the point where we have kind of some standardization across this kind of API framework. So that's what we've been working on, or at least what we envision and what we're trying to do. So.
All right, thanks, Scott. Well, 3 very different presentations about many different aspects of data preservation there. So why don't I go ahead and open it up for questions if anybody has any.